Welcome to Math with Professor V, and this is the video series Algebra Review for the Calculus Student. So in this video, we're going to review the laws of exponents for a calculus student, and then see how we use these laws of exponents when we need to apply our differentiation rules and techniques. So starting off, this is an algebra video, and then in the second half, I'll work through examples from your calculus class, taking derivatives of functions and applying all of the rules that we reviewed in the beginning. So let's just make a list now, that way you can have it handy as you work through your calculus exercises. Here are some of the laws of exponents. If you have a raised to the m times a raised to the n, the base is the same and you add the exponent. So you have a to the m plus n. And this should make sense. I'll write out an example. Like when you have x squared times x cubed, applying this rule, that would give us x to the fifth. Now, if you wanted to do this the long way, x squared is x times x, and then x cubed is x times x times x. So if you just sit there and count them up, yeah, it makes sense. There's 5 of them, but who's going to do that all day? Not me. Just add the exponents. Next rule, a to the m divided by a to the n. Pretty similar. You have a to the m minus n. It's always numerator's exponent minus denominator's exponent. We can work through our example here as well. Say you have x to the fifth over x squared, and you wrote each of them out expanded. X to the fifth means you have 5 x's. X squared means you've got 2 of them. And then yes, 2 x's from the numerator cancel with the 2 x's in the denominator. And how many do I have left up top? Just 3. Well, how else could I have gotten there? 5 minus 2 is 3. Okay. Good. Next rule, a raised to the m, all of that raised to the n is a to the m times n. So a lot of the time students confuse these two rules, 1 and 3. Notice in 1 you have 2 terms, right? The base is there twice with 2 different exponents. In this case, in 3, you only have 1 base. It's raised to a power, and then that whole quantity is raised to another power. So let's just look at an example really quickly. Like if you have x squared cubed, that ends up being x to the 6th. You multiply these 2 numbers. And the reasoning behind it is x squared cubed means you have x squared 3 times, right? And multiplication is repeated addition. So 2 plus 2 plus 2 is 6, which is just 2 times 3. Okay, the rest of the rules have to do with distributive property, basically. So when you have a times b raised to the n, that n distributes, and it's a to the n, b to the n. A divided by b to the n is a to the n over b to the n. A to the 0 is 1, provided a is not 0. If you have 0 to the 0, that's an indeterminate form. And then a to the negative n is 1 over a to the n. Okay? Now, most of the time in calculus, you're actually going to go the other way. So if you see something with an exponent in the denominator, you want to rewrite it with a negative exponent, and we'll talk about that when we start working on taking derivatives, okay? But just be able to go back and forth. So this is the basic list, and we're actually going to add a little bit more to it, okay? So what does it mean when our exponent is a fraction? So for example, I want you to consider if you have 9 to the 1/2 power. I can rewrite 9 as 3 squared, right? And then keep that 1/2 out there. And then using our laws of exponents, in particular, number 3, I would multiply those 2 exponents. So I would have 3 raised to the 2 times 1/2, which is just 3 to the first, right? Which is 3. So look at that. We had 9, we raised it to the 1/2 power, and we ended up with 3. So that's the same as just taking the square root of 9. That would give us 3. So from this, we can observe that if you have some quantity a raised to the 1/2 power, that's the same as taking the square root of a. And when we take the square root, The little number here is called the index. It's a 2, and we don't usually write it. It's assumed to be 2 when you don't write anything. But as you know, we can take different roots, not just square roots. We can take a cube root or a fourth root. So here's exponent rule number 8, a little bit more generalized, okay? If you have a raised to the 1 over n, that is equal to the nth root of a. And I'm going to give you a little bit of vocab here, okay? So this number n, that's called our index. A, the stuff underneath the radical, is the radicand. And so I want you to notice that the denominator of the exponent becomes the index, and the base becomes the radicand. Okay, so whatever the denominator is here, that's the index. The base is the radicand. So for example, if you had cube root of b, that's the same as b to the 1/3. If you had the fourth root of x, that's x to the 1/4, so on and so forth. Okay? This is very important to be able to do in calculus because this is how we apply our differentiation techniques. So now let's just practice writing an equivalent expression using radical notation, and then we'll go the other way. We're just going to go back and forth between the two notations. So 25 to the 1/2 power, that's the same as square root of 25. And then I can simplify that, that's just 5. Not plus or minus 5, just 5. Okay, negative 25 to the 1/2. I want you to notice this negative sign is not in parentheses with the 25. So it's not going to go underneath the radical. It's going to stay outside. It's like a -1 times 25 to the 1/2. So then that's just going to be -1 times the square root of 25, which is -5. How are we doing? Okay, good. 64 to the 1/6. Notice the denominator is a 6. So that's going to be my index. This is the 6th root of 64. And maybe it's scaring you. You're like, I don't know my 6 roots. But you know, 64 is not a big number. It probably wasn't a big number to begin with that was raised to the 6th. It's just 2 to the 6th. 2 to the 6th is 64. Yeah, so if I take the 6th root, I just get 2. Okay, excellent. Now let's try going the other way. This is what you're going to do in calc all the time. Write an equivalent expression using exponential notation. Cube root of 19. We're going to rewrite that as 19 to the 1/3 power. And that's it. Just leave it. That doesn't simplify or anything. Square root of a to the 5th. If you need to remind yourself that there's a little 2 there, that might be a good idea. So this is a to the 5th raised to the 1/2. And then remember, we can simplify. We can multiply these exponents by each other. So this is going to be a to the 5/2. Beautiful. Example C, we have the 5th root of a. So that's a to the 1/5. All right. Good. Now we're going to add one more exponent rule to our list. Okay. And I want you to consider the following. If we have x to the 2/3, there's 2 ways you can think about this. You could think of it as x to the 1/3 squared, which if I rewrote that using radical notation, it would be cube root of x squared. Or it could be another option, x squared raised to the 1/3, in which case you have the cube root of x squared. Both are the same. Both are the same. So here's exponent rule number 9. If you have a to the m divided by n, you can write it as the nth root of a to the m, or you could write it as the nth root of a all raised to the m. They're equivalent. I'm going to tell you right now, though, this is the version that I use mentally when actually trying to evaluate what some number is raised to the m over n. So I recommend you use this one, when you're mentally computing. Okay, and we'll work through an example right now so you can see what I mean. Okay, here we go. So write an equivalent expression using radical notation and then simplify. So we have 9 to the 3 halves. 9 to the 3 halves. First, let's do the version that I said. You're going to take the nth root of a, so you're going to take the square root of 9 and then raise it to the third. So that would be 3 raised to the third, which is 27. Boom. See how painless that was? If you went for the other option, notice what the problem would be. You would have the square root of 9 cubed. And already I'm like, oh, goodness gracious, 9 cubed. So now I need the square root of 729. If you even were able to make it that far. And then that comes out to, yes, it is 27 as well. But I mean, which way was less painful? It's always easier to take the root and make the base smaller and then raise it to the numerator and then make it bigger instead of making it bigger first and then trying to figure out whatever root it is, okay? So that's why I recommend that you use this version here. And I'll use that for the rest of the examples. I won't do both ways for all of them anymore, okay? All right, negative 16 to the 3/4. Again, this minus sign is not in parentheses, so it's just being attached on the outside of everything. So you just have negative. This is going to be 4th root of 16, and then all of that is cubed. So 4th root of 16, that's 2 cubed. 2 cubed is 8, and then we have a minus sign sitting out there. So this is negative 8. Beautiful. Now this next one here, all of 4y to the 6th is going to go underneath the radical. So we have here radical 4y to the 6th. Notice the 2 in the denominator. That means I'm taking a square root. You can write it or not write it. It's not that big of a deal. And then all of this gets raised to the third. Okay. So we're going to assume all variables are positive, so we don't have to contend with absolute value. And then here, square root of 4y to the 6th, that's going to be 2y cubed. And then all of that gets cubed. And then don't forget, we have another property that tells us we distribute that exponent. So then we have 2 cubed times y cubed cubed. And this ends up as, very good, 8y to the 9th. Beautiful, beautiful. Okay, let's practice just a little bit more, different scenarios. Write an equivalent expression using exponential notation. So if you have the 4th root of m cubed, that would be m to the 3/4. That's it. Cube root of x squared, that would be x raised to the 2/3. The index becomes the denominator. That one's done. Fab, fab, fab. Next one, 6th root of 2a to the 5th b, all raised to the 5th. You just take the radicand, and then the exponent's going to be 5/6. And I'm not cleaning up anymore. All they said was just write an equivalent expression. So that's all I'm doing, okay? Now, recall the rule for negative exponents. This means that a raised to the negative m/n is equal to 1/a to the m/n. Okay, so we're going to practice now working with some negative exponents a little bit. They come up quite frequently. And as a note of caution, a negative exponent doesn't mean that the expression itself is negative. Okay, so let's simplify completely. Here we have negative 25 to the 1/2. And you see how this time finally the negative is in parentheses with the 25? That means it's going to go underneath the radical too. So we're taking the square root of negative 25. And I'm just going to stop right here. This is not a real number. And don't worry, when you're starting your calculus course, you're not going to work with imaginary or complex numbers. That's way, way later in your math career, okay? So we're done with that one. Yeah. 25 to the negative 1/2. Right away, rewrite this as 1/25 to the 1/2. Then you can write this as 1 over square root of 25, which is 1 over 5. Now, I'm going to be honest, in calculus, if you go straight from here to here, no one will be upset. You don't have to rewrite it with the radical. I'm just showing it now so that we get more comfortable, okay? And then example C, this time you see how the negative is not in parentheses with the 25? Yes, so then it's like a negative 1 being multiplied by 25 to the negative 1/2. So then this is just negative 1 times 1 over 25 to the 1/2. And that's negative 1 times 1 over square root of 25. We know that that's 1/5, and then we just have a minus sign in the front. So our final answer is negative 1/5. Beautiful. Now, just keep in mind, all of the rules of exponents still apply when the exponents are rational. So they don't have to be integers in order for us to add them or subtract them or apply any of the rules that we reviewed in the beginning of the lesson. So let's just practice a little bit. If you have 5 to the 2/3 times 5 to the 4/3, the same rules apply. We add these exponents together. So this is going to be what? Let's see, 5. 2 plus 4, that's going to be 6 divided by 3. This is 5 squared, which was 25. Ooh, that cleaned up so nicely. Okay, next one, example B. I'm going to simplify just the numerator first. So I'm going to add these exponents together. X to the negative 3/4 plus 5/4 is x to the 2/4. And then I have over x to the negative 1/4. And then remember the rule when you're dividing, you take the exponent from the numerator and you subtract the exponent from the denominator. So I'm going to write it out slowly. It's x to the 2/4 minus negative 1/4. Oh, yeah. So then it becomes addition, right? And then this is going to be x to the 3/4. Perfect, perfect. Very good. Now, it's often possible to simplify a radical expression by rewriting it using rational exponents, use the rules of exponents to simplify, and then go back to radical notation. So you'll see what I mean. It sounds like a mouthful, but basically you use rational exponents as a tool to help you simplify. And the following example says, use rational exponents to simplify. Do not use fractional exponents in your final answer. So what that means is they want us to go back for our final answer to using radicals. Okay, no big deal. So let's practice a few, and then we're ready to do the calculus now with all of these lovely rational and radical exponent rules refreshed in our mind. So 4th root of 9 squared, that's not simplified. I can rewrite it as 9 to the 2/4. And then, oh, that reduces. That's 9 to the 1/2, which is square root of 9, which is 3. Okay, that's done. Next one, 7th root of xy to the 14th. So start off, you can rewrite this as xy raised to the 14 over 7, right? So that's xy raised to the 2nd power. And then we know we can distribute that exponent through. So this ends up as x squared y squared. Perfect. There we go. There we go. Now I'm happy. Last one, the 5th root of the square root of 2a. Don't let this one scare you, the double radical situation. Square root of 2a is 2a to the 1/2. And then I have the 5th root of all that. So all of that is raised to the 1/5. And then just think back to your rules. You don't have to invent any new ones, I promise. 1/2 times 1/5 is 1/10. So I have 2a raised to the 1/10. Okay, then you can just rewrite this as the 10th root of 2a. And then that's simplified. There is a wee bit of a shortcut. I want you to notice something. Are you ready? Notice we had the 5th root of the square root of 2a. Well, if I just multiply the indices, then you have 5 times 2, that root of 2a, which gives us the 10th root of 2a. And yes, that always works when you have those nested radicals like that. So multiplying the indices here is equivalent to when we multiplied them here. It just saved you a few steps. Okay? How are you guys doing? Hopefully it's all kind of coming back to you. It's just the sort of thing with math, if you don't use it consistently, you lose it. And that's normal. That's nothing to feel bad about, which is why, I always give my students speeches on how they should tutor other people in math, because it just helps you refresh and stay sharp. So now, how is this all going to apply to calculus? Well, we need to often rewrite functions involving radicals with rational exponents so we can take their derivatives. And I'm just going to jump right in. I'm not giving you a lecture on what a derivative is or what the differentiation rules are. We're just going to practice. If you need a video lecture, though, I'll have them all linked in the description. So differentiation rules, product rule, quotient rule, chain rule, all of that. We're just going to go for it right now, okay? Differentiate the following functions: y equals x squared minus 2 rad x over x. Now, I'm not going to use the quotient rule because I'm noticing in the denominator, I just have one little x, and I can actually clean this guy up and just take the derivative directly. So I don't want to use product rule, quotient rule, all the fancy rules unless absolutely necessary. And it's not necessary right now. So let's rewrite this. This is x squared minus 2x to the 1/2 over x. And then I can write the denominator separately under each of the terms in the numerator. So I can rewrite this as x squared over x minus 2x to the 1/2 over x. Okay, so then y equals x squared over x, that simplifies to just x, minus, and then now, okay, we're going to use our rules of exponents. This is x to the 1/2 in the numerator, x to the first in the denominator. You do 1/2 minus 1. So we're going to have 2x to the negative 1/2. I haven't done any calculus yet. I'm just rewriting the function. So it's in what I like to call derivative friendly format. Now I can just go term by term to differentiate. So y prime, or dy dx, derivative of x is just 1. And then minus 2, keep the exponent, keep the coefficient, it just comes along for the ride. You bring the exponent down front, multiply by it. So I'm going to have a negative 1/2 x, and then the new exponent I find by subtracting 1. So what does this turn into? 1. These guys are going to cancel, right, into positive 1 plus x. Negative 1/2 minus 1 is negative 3/2. That's my new exponent. And then you can leave it like this, but most of the time we rewrite it as 1 plus 1 over x to the 3/2. So there's our derivative. Okay? So you see how all of our laws of exponents are in play the entire time. Okay, let's try another. G of x equals the square root of x plus 1 over the cube root of x squared. So first, before we take the derivative, let's rewrite it using rational exponents. So I'm going to write this as x to the 1/2 plus x to the negative 1/3 squared. Now you could do the chain rule, but instead, why don't we just expand or multiply this all out? So x to the 1/2 plus x to the negative 1/3 squared, that's going to be the first term squared plus 2 times x to the 1/2 times x to the negative 1/3 plus the last term squared. Where am I getting that? That's the rule for how you square a binomial without sitting and writing it out twice and foiling it. If you have the quantity a plus b squared, it's a squared plus 2ab plus b squared. So basically this is a, and then this is b. Your other option, if you didn't know this, was just to write out this twice and FOIL, but this is much faster once you get the hang of it. So I recommend you practice it if you don't know it yet. Okay, here we go. Let's clean up now. X to the 1/2 squared. So I multiply these exponents. That's just going to be x to the first plus 2 times, I'm going to add these exponents. So it's x to the 1/2 minus 1/3. If you need to do it off to the side, fine. This is 3/6 minus 2/6, which is 1/6. So here's the exponent. Plus, and then again here, we multiply these, so we'll have x to the negative 2/3. Good? I've done no calculus. This is just g of x still. Now let's take the derivative. It's in derivative-friendly format. So g prime of x, derivative of x to the first is just 1. Plus, this is going to be 2 times 1/6 x to the, you always subtract 1 to get the new exponent. So 1/6 minus 1 is negative 5/6. Plus, this is negative 2/3 x to the negative 2/3 minus 1. So negative 2/3 minus 3/3, negative 5/3. Okay, let's clean up a wee bit more. This is 1 plus 1/3 x to the negative 5/6 minus 2/3 x to the negative 5/3. And then probably we should just put all the negative exponents in the denominator. So 1 plus 1 over 3x to the 5/6 minus 2 over 3x to the 5/3. Good? Okay, beautiful. Let's practice some more. I taught you so many rules, we got to use them all. Now we're going to use the chain rule to find the derivative of this function, because 1 plus x to the 4th raised to the 2/3, I can't expand that nicely before I take the derivative. So we're going to do the chain rule. So if you need to review the chain rule, I have several videos linked in the description. But basically, you differentiate the outside function and then you work your way in, multiplying by successive derivatives. So bring the 2/3 in the front. And then the new exponent, 2/3 minus 1, would be negative 1/3. And then you don't touch what's inside just yet. And then you apply the chain rule and you multiply by the derivative of the inside. So the derivative of 1 is just 0, and then the derivative of x to the 4th is 4x cubed. Okay, and then let's see, what can we clean up? So these two guys we can multiply by each other. I'll keep just the 2 times 4x cubed, that's 8x cubed, and then that 3 from the 2/3 is going to go in the bottom with 1 plus x to the 4th. To the positive 1/3 now, and then that's completely simplified. All right, good. So again, 2 times 4x cubed, there's my 8x cubed, and then this 3 just went downstairs with this whole guy because he had a negative exponent. Okay, let's practice some more. Let's get a little trig up in here. F of t equals the cube root of 1 plus tan t. So before you even think about taking the derivative, you want to rewrite it as 1 plus tan t raised to what power? Very good, the 1/3 power. Okay, so f prime of t is going to be, we have to use a chain rule again. Bring the 1/3 down front. The new exponent is 1/3 minus 1, so negative 2/3. What goes inside the parentheses? Exactly what you see. Don't touch a thing. Then I'm going to use the chain rule, multiply by the derivative of what was inside. So derivative of 1, 0. Derivative of tan t is secant squared t. This is super similar to the last one. So secant squared t is going to stay in the numerator. And then I'll put 3, 1 plus tan t to the positive 2/3 in the denominator now, okay? Good, 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 good. Here we've got a little bit of a spicier one. I think it's time, you guys can handle it. So y equals x squared plus 1 times the cube root of x squared plus 2. So let's rewrite it with rational exponents. So this is x squared plus 1 and then x squared plus 2 to the 1/3. We do need to use the product rule, right? So you could think of this is f and this is g. So you'll have f prime times g plus g prime times f. or whatever order, as long as they take turns taking the derivative, okay? So y prime is going to be f prime, derivative of x squared plus 1 is 2x, times g, I leave it alone. So x squared plus 2 to the 1/3. Plus, now I do derivative of g. So derivative of x squared plus 2 to the 1/3, I bring the 1/3 in the front, leave this alone. The new exponent is negative 2/3, 1/3 minus 1. And then don't forget, you have to do the chain rule and multiply by the derivative of what's inside. So derivative of x squared plus 2, that's just 2x. So that's all g prime. And then I have to multiply that by f. Okay, let me write underneath what everything is. Maybe that'll help you too. So this is f prime g. All of this is g prime, and then that's f. Okay, so how should we simplify from here? If you've watched my Calculus 1 video lectures, I showed a method of factoring out the greatest common factor. If you want to go check it out, I have that video linked in the description. That can be confusing for a lot of students. So lately I've been showing it a different way. And basically it starts off by rewriting all of the negative exponents in the denominator. Okay, so this first term has no negative exponents, so I'm just going to leave it alone. And then this second term, it does have negative exponents, so I'm going to rewrite it x squared plus 2 to the 2/3 in the denominator, and the 3 will go down there with it. So let's just keep 2x here, x squared plus 1, and then we have 3x squared plus 2 to the 2/3, okay? Now I want you to focus on getting a common denominator. So this first term is just over 1. The common denominator is exactly what you see right here, 3 times x squared plus 2 to the 2/3. So this guy is missing all of that. 3 times x squared plus 2 to the 2/3, top and bottom. Okay, and then let's see what we have now. So 2x is untouched. There's a 3 in the front. And then good thing we reviewed our laws of exponents, because you have x squared plus 2 to the 2/3, x squared plus 2 to the 1/3. You add those exponents, 2/3 plus 1/3, that's 3/3, which is 1. So then now I just have x squared plus 2 to the first. Are you guys okay? 3, 2x, and then these two I can combine. I just add the, oops, I was like on an erasing frenzy. Calm down, Professor V. Add these exponents together, boom. Good, right? This guy we didn't have to touch because it already had the LCD, so we're good. 2x, x squared plus 1. And then now the denominator is 3 x squared plus 2 to the 2/3. Okay, very good. To simplify further, I wouldn't distribute everything out because notice I can factor out a 2x from both of the terms in the numerator. Do that, it'll make life nicer. So we have 2x times 3 times x squared plus 2 plus x squared plus 1 over 3 times x squared plus 2 to the 2/3. And then now go ahead and just distribute and clean up inside. So this is what? 2x times, that's 3x squared plus 6 plus x squared plus 1 over 3 times x squared plus 2 to the 2/3. We're almost there, guys. We're almost there. 2x times 4x squared plus 7 over 3 times x squared plus 2 to the 2/3. And you know what? I wouldn't even bother learning the other way with factoring out the GCF. It's tricky to do with negative exponents. This will work just as well, and I think it's so much more straightforward, so enjoy. That's what's great about teaching, is that you can see what methods work well for students and then refine them. Okay, last example. What rule have we not used? That's right, the quotient rule. Do you know the song for the quotient rule? No? I'll link a video where I sing it for you. Not really. I'm kind of more like reciting it. You don't want to hear me sing. I won't put you through that. Okay, the numerator is high. We call it high. The denominator is low. So it's low d high minus high d low. Square the bottom, away you go. Okay. So here we go. G prime of y is going to be low d high, which means the denominator, times the derivative of the numerator. Derivative of the numerator would be 4 times y minus 1 cubed, that's low d high, minus high means numerator, leave it alone. D low is derivative of the denominator, so chain rule time, 5 times y squared plus 2y to the 4th, and then derivative of y squared plus 2y is 2y plus 2. And then you have low, low, or square the bottom, away you go. So y squared plus 2y to the 10th. Good. Okay, now again, don't start multiplying out the numerator. That would be insane. It would spiral out of control and you would just start crying, and we don't want that. There's no tears in calculus. We're going to factor out the GCF. I see y squared plus 2y to the 5th, y squared plus 2y to the 4th. I can't take out any more than what one of them has, so I can only take out 4 of them. That's fine. I'll take it. Here's a 4. I mean, there's this 2y. I don't want to mess with it. That'll make a mess. And then y minus 1 cubed, y minus 1 to the 4th. I can only take out the smaller exponent, so let's do it. Okay, so what's left? I want you to recognize there's 2 terms. 1, 2. So if I took out y squared plus 2y to the 4th, from here there's only 1 left. Y squared plus 2y to the 1st. The 4 is still there. And then this y minus 1 cubed is gone because we took it out. Minus y minus 1 to the 4th. I took out 3 of them. I still have 1. This 5, he's still there. Nobody touched you. Okay. Poor little 5, just hanging on for dear life. This is completely gone, right? I took it out, and then I still have 2y plus 2. Okay. Over y squared plus 2y to the 10th. Anything you notice? Good, yes, this we can cancel with the denominator, and now there's only 6 of them. I love it. So then what do we have? We have y minus 1 cubed. I think we should just start multiplying everything out over here. Ba-doom, ba-doom. That's going to be 4y squared plus 8y minus, can I show you something cool? 2y plus 2 is 2 times y plus 1. So really over here I have 5 times 2, that's 10. Do you guys know what y minus 1 times y plus 1 is? Those are conjugates. It's going to give a difference of squares. That's y squared minus 1. And you're totally allowed to like reorder how you multiply things. Multiplication's commutative, which makes it so beautiful. And then this is y squared plus 2y to the 6th down here. Oh, fabulous, fabulous. Okay, so this is going to be, let's see, y minus 1 cubed. This is 4y squared minus 10y squared, so that's negative 6y squared plus 8y plus 10 when I distribute over y squared plus 2y to the 6th. Is that as cleaned up as it's going to get? I mean, we could take a 2 out of all of these guys. Should we do it? Let's do it. And I'll just put it all the way out front. So we'll have 2 times y minus 1 cubed. And then I'll have negative 3y squared plus 4y plus 5, because I took that 2 out from everybody. And then we have y squared plus 2y to the 6th. Okay, good. This problem didn't really use laws of rational exponents, but just more simplifying, factoring, and stuff that I thought would be helpful. Okay, anyways, I hope this video really sharpened your skills if that was what you were looking for. Don't forget to give it a thumbs up. Leave me a comment down below. What math class are you taking right now? Is it Calc 1 or are you just watching for pure entertainment? Or are you in Calc 2 and finding yourself in need of review of these basic concepts? Anyways, I love you all so very much, and I have more content coming soon. Don't forget to follow me on Instagram and TikTok. Did I say subscribe? Please subscribe. Please help my channel grow. I get so many lovely comments from students who are not my own students that I teach around the world who find my videos helpful, and I just would love it if my channel could grow so I could help even more students learn calculus more easily. Anyways, that's pretty much it, and I will be back sooner than later. If you need a video lecture on any topic in Calc 1, 2, and 3, I got you. So just check out the playlist and keep working hard, guys. All right, bye.